Hello again, everybody. Welcome back to another lecture. This time we're going to be talking about improper integrals. Now, these aren't integrals that, use the wrong fork when they go to a fancy dinner or anything like that. These are integrals that, well, they have something wrong with them, but not just improper in the sense that they don't behave correctly. Improper in the sense that there's something just fundamentally weird about them because they violate what we usually think of as the definition of an integral. We have to do some redefining to make this kind of thing work. Here's what I mean. So we know how to handle something like the integral from 1 to 3 of 1 over x squared. Right? That's just the area under the curve. We talked about that a lot when we were breaking things up into little pieces, letting the pieces get smaller and smaller, and in the limit, that's the definition of what an integral is. So this integral from 1 to 3 means taking the interval from 1 to 3, breaking it up into little pieces and adding up the pieces and so on. But what if I wrote an integral like the integral from 1 to infinity? I mean, what does that even mean? Because you see what the problem is. I can't take the interval from 1 to infinity, that's infinitely long, and start breaking it up into pieces and adding up the pieces. Because as soon as I do, I need infinitely many pieces. And what do I do to add up infinitely many pieces? Of course, this is our first step toward doing exactly that. How do you add up infinitely many numbers? And that is all of what series are about. So series is what we're going to spend our time talking about for the entire last third of this course. And this is sort of our first step in that direction. But it clearly doesn't make sense right now to talk about breaking an interval from 1 to infinity, it's infinitely long, into pieces, and then adding up infinitely many pieces, right? We could add up finitely many pieces and then just take more and more and more of them. We can't add up infinitely many numbers right now and have that make sense. In fact, we won't ever do that. We'll sidestep this issue in sort of the same way we're about to do now. What we do is we define what this means, this integral from 1 to infinity, to be this. We integrate from 1 to some big number, call it like capital N. And that makes perfectly good sense, right? This integral from 1 to capital N, that's just a regular old integral. It's an area under a curve from 1 to capital N. We know what that means. That's just a regular old integral we've always done. So you do that and you get a number. Then you let n get bigger and do it again. And let n get bigger and do it again. And as n gets bigger and bigger and bigger, then that's what we call the integral from 1 to infinity, that limit. Right? So it's really important to realize that this is a limit. It's really important when you work these sorts of problems to include the limit and not just skip over that as though infinity were some kind of a number that we could just plug in using the fundamental theorem of calculus, because it's not. And things go really wrong and weird if you start to treat infinity like a regular old number. Well, this is our first example of an improper integral. We'll have a few more kinds of improper integrals as we go along, but first I think we desperately need some examples. So here's one. Integral from 1 to infinity, 1 over x squared. Okay, so this is easy enough to integrate because 1 over x squared, that's really x to the negative 2 power. We can integrate 1 over x to the negative 2 power, not going to be a problem. Always remember, though, that this is an improper integral and we have to treat it like that. So we really want to write down limit as n goes to infinity and write down the integral from 1 to n. If you don't do that on the homework and you don't do that on the exams, then you'll lose some points because it's that big of a deal. Okay? So make sure that you write down the limit step because it's that big of a deal. Okay, so now when we want to do this integral, that we actually know how to do now, integral from 1 to n of 1 over x squared, that's pretty easy. It's x to the negative 2. When you integrate it, you get negative x to the negative 1. Right? So x to the negative 1 is 1 over x. So what we end up with is negative 1 over x as the integral. Okay? Now I just need to plug in the 1 and the n into that, and we're off to the races. So negative 1 over x, I plug in the capital N, I get negative 1 over n. Negative 1 over x, and I plug in the 1, I get negative 1 over 1. Okay? So far so good. This in the parentheses is what the integral from 1 to n turns out to be. Again, that's just a regular old number. I mean, if you give me a value of n, like 5 million, I can plug that in for n and get a perfectly good number over here. So the cool thing is, if I let n get bigger and bigger and bigger and bigger and bigger, then what happens to this integral? Well, what happens to if n is, say, 5 billion, then 1 over 5 billion is 5 billionth. To be careful with my microphone, not spit here. 5 billionth, which is really, really small. So 1 over a big number is actually a really, really small number. So this 1 over n here is going to go toward 0 as n gets really big. So this first part goes to 0. The second part is negative, -1, which is just plus 1. So the whole thing becomes plus 1. That's awesome. This improper integral, which looked weird and freaky, is just 1. This means that the area under the curve, 1 over x squared, from 1 all the way out to infinity, all that infinitely long stuff, right? That infinitely long strip, right? The area under all of that is just 1. Okay? On the other hand, here's an integral that looks like it ought to be the same, 1 over x, right, from 1 to infinity. And if you remember the graph of 1 over x and the graph of 1 over x squared, when you draw them by hand, it's really hard to tell them apart, right? They just start out at 1 and they drop off toward the x-axis. So how do we deal with this, right? Well, again, first step, always, always, always write it as a limit as n goes to infinity, and then integrate from 1 to n. Again, this is super important, and if you don't write this and you just start plugging in infinity as though it were, an actual number and trying to write the limit down and integrate it and just stick in infinity as though it were a number, you'll lose points on the exam. Okay, 1 over x, that's easy to integrate. That's just natural log, so of absolute value of x. So natural log of absolute value of x, I plug in the n and I plug in the 1. Right? Now I need to know what happens here as n gets bigger and bigger and bigger. Well, this turns out to be infinity. Okay? Um, the reason is you may or may not remember from ages back in algebra when you were looking at graphs. But natural log, the graph of this gets bigger and bigger as you plug in bigger and bigger numbers. So as you plug in bigger and bigger numbers into natural log, this gets bigger and bigger, and the whole thing goes off to infinity, which is weird, right? Because the graphs look kind of similar when you graph them. And one integral has an area of 1, the other integral has an area of infinity. Okay? Well, okay, this is weird. Dealing with infinity is weird, right? And we have to be super careful with this. Well, we at least need a name for this kind of phenomenon, right? So if this limit is finite, like in the first example where we got a 1, or if the answer turned out to be negative 500, whatever it is, if it's just a regular old number, then we say that that improper integral converges. Otherwise, like in the second case where we got infinity, or if we get something weird where the limit doesn't exist for any reason, we say that the integral diverges. These two words, of course, are going to show up a lot in the last third of the course. Once we start talking about series, the big question we're going to ask over and over and over about series, whatever those are, we'll get to that in the last third of the class. But what we're going to be asking the question over and over and over about them then is, does this series converge or diverge? It'll be the same words and a similar sort of meaning. Well, notice that if our integral is going to converge, like the first one did in the example we had on the last page, 0 has to be a horizontal asymptote for the graph. If the area underneath the graph is going to be a finite number, then that graph has got to get really small really quickly. Because if we're going to be adding up more and more and more and more area as we go further and further and further out along the axis here, then we've got to be adding up less and less and less as we go along. If we keep adding, say, 1 unit of area every time, there's no way we can keep adding ones and it converge, right? It'll keep the area will keep getting bigger. But if the area under the curve keeps getting smaller and smaller and smaller, you can imagine how, like in that first example, the area will actually be finite. Okay, so here's a really important fact. Those first two examples that we did are examples of this rule. And this is important enough that I'm going to put it here and call it a fact and say this is something that you should have memorized. So this is a rule that we're going to need a lot later. I mean, a whole lot later. Big flashing lights, you must know this. So it's worth putting it up here and saying you must know this fact, and I'm going to take a few minutes to explain why it's true. So if you have an integral that's like 1 to infinity, and you have 1 over x to the p, right, where p is some number, that integral will converge if and only if, that's what that little arrow there that goes back and forth means. It converges if and only if the p is bigger than 1. So in that example we had a few minutes ago, you see why this worked the way that it did. With 1 over x squared, right, our p here is 2. And the p was 2. We worked through all the details. The limit turned out to be 1 in the end. This integral converged. On the other hand, 1 over x, the power there is 1. So the p is equal to 1. And the rule says you converge when the power here is bigger than 1. The power was exactly equal to 1. We should diverge, and sure enough, we do. We got infinity there for the limit. Okay? So that's a super important fact. Okay, and so why should this be true? Well, let's just go through and do a little calculating. So the integral from 1 to infinity of 1 over x to the p, well, first step, always write this using the limits, right? So we write this as an integral from 1 to capital N, and then take the limit as n goes to infinity. And I'll also do a little algebra here. That 1 over x to the p, let me write that as x to the negative p, right? That may make it a little easier. Because now when I integrate x to the negative p power, how do I integrate it? Well, when you integrate x to a power, you have to add 1 and then divide by the exponent. So what I'm going to get is x to the negative p that I had before, but I have to add 1 to it. So I'll have x to the negative p plus 1. Then I need to divide by this exponent. So I'll have 1 over negative p plus 1. And again, the number here doesn't actually matter very much when I start taking the limit. But you see what's going to happen. Oh, by the way, I should say before we, maybe you see what's happening, but if I don't say this, I'll forget to. In the red box here, this works if p is not equal to 1. Because remember, what happened when p was equal to 1? We did that example a second ago. When p is equal to 1, I've just got 1 over x. When you integrate it, you don't integrate it this way. 1 over x, you integrate it and you get a log. Right? Because if p were 1, then negative 1 plus 1 would give me a 0 power here. And that doesn't work. When you integrate 1 over x, you get log. And we already saw that guy diverges, so that fit the pattern. Otherwise, what happens here, right, when p is not 1, so this is the right way to integrate this integral, what's going to happen when I take the limit? Well, you see, and again, maybe everybody has already seen this, since I've said, obviously you see. And if you didn't, you may have paused the video to wait until you did. What's going to happen here is if the p is bigger than 1, so let's imagine what happens. If p is, say, 2, then I would have negative 2 plus 1. The whole thing becomes negative 1. In other words, the exponent here is negative, which means that this is really x in the denominator. And as we saw a few minutes ago when we took the limits, well, when you have a big number in the denominator, because I'm about to plug in the capital N and let the n get really big, when you have a big number in the denominator, it goes to 0. Okay? So what will happen is if p is bigger than 1, then negative p plus 1, right, will give us a negative number. This means that x is in the denominator. When I plug in the capital N, it's going to go to 0 when n gets really big. On the other hand, if p is less than 1, right, like say a half, then negative a half plus 1, oh wait, that's like positive a half. Suddenly this power has now become positive, which means it stays up in the numerator, doesn't go down the denominator, and now my big number is on top of my fraction, and that means that my big number is a big number. Instead of, being in the denominator where it makes things smaller, it stays in the numerator where it makes things bigger. This means that the whole thing gets bigger and bigger and bigger, and the limit goes off to infinity. So that's why the super important fact is true. Because in a world full of fake news and people arguing over over what's a fact and what's not, okay, here's a fact. And now I hope everyone believes why this fact is true, that if you have an integral of from say 1 to infinity of 1 over x to the p, this will converge whenever the p is bigger than 1, and it diverges whenever the p is 1 or smaller. By the way, the integral from 1 to infinity was not the key thing here. This could have been an integral from, say, 5 to infinity or 7 to infinity or a half to infinity. As long as this was a positive number, right? Because at 0, obviously, I've got problems dividing by 0. So I just need this to be some positive number. Then I'll still get the same rule. The next kind of integral we want to talk about are integrals that run from minus infinity to infinity. So something like this. Integral from minus infinity to infinity of 1 over 1 plus x squared. Okay, so this is really weird too, because it looks like maybe what the thing to do would be to just let capital N go toward negative infinity and go toward plus infinity, and we just do both at the same time, sort of. But that's a little tricky, and it also causes technical problems where things exist where we don't want them to. Because remember, we have to be really careful when we deal with infinities. So here's what the definition of an integral like this is. The definition of an integral that goes all the way from minus infinity to plus infinity is this. You break it somewhere. It actually doesn't matter where. 0 is the most obvious number halfway between plus infinity and minus infinity, and 0 is usually an easy number to plug into stuff. So I'll generally use 0 as my breaking point. But just break it somewhere, and then you do each piece separately. Right? So I will integrate from negative infinity up to 0, and I'll integrate from 0 up to positive infinity. The reason we want to do it this way is if you don't, if you tried to go from, say, negative n to plus n, and then let the n go off to infinity, then you might have like infinitely much positive area on one side and infinitely much negative area on the other side, and they cancel each other out. In other words, what you want to avoid is having, say, this integral that I've done from negative infinity to 0 turn out to be, a huge positive number, and say this integral turn out to be a huge negative number. And when you add them, if you were to integrate them both together, you wouldn't notice that they cancel each other out in the integral. But for this to exist, both integrals have to exist. That's why we always break it and we do each piece separately to keep something odd like that from happening. So the rule is an integral from negative infinity to infinity means you have to break it somewhere in between, almost always at 0. Go from negative infinity to 0, then go from 0 to infinity, and do each piece separately. And this is not a hard integral to do, because we remember 1 over 1 plus x squared. Well, that integrates nicely. That's just inverse tangent when we do the integral. So we will integrate from, say, n to 0. Right? When we integrate that, we get an inverse tangent, and we let the capital N go off to minus infinity, inverse tangent of 0, minus inverse tangent of the capital N. The other integral is going to be the same sort of thing. We get an inverse tangent, and then we plug in the capital N, then we plug in the 0 and subtract them. And let the capital N go off to plus infinity. Right? So, again, just like what the examples we've done before, we have a capital N sort of integral. The first one is from capital N to 0, and then we let the capital N go off to minus infinity. The second integral is from 0 to capital N, and we let the capital N go off to plus infinity. Now, what may be a little weird here that you haven't seen or thought of recently is what happens with an inverse tangent, right? The graph of inverse tangent may be something that you've forgotten and haven't had to worry about very long. So I'm going to show you the graph. So the graph of inverse tangent, there it is. That makes it really easy to see what inverse tangent of 0 should be, of course, because inverse tangent of 0, well, right there, should be 0. Okay? It's also, well, maybe not easy because of the way the graph is labeled here, but I think you'll believe me that as you let n go off to infinity, then this graph seems to level off, right? Looks like it's got a horizontal asymptote, or like around something like 1.5. It's not 1.5. If you think about it, see what it's got to be. It's not 1.5. It's pi over 2. Because remember, pi is 3.14-ish. So half of that would be, you know, what, 1.57-ish. So you see why it looks a whole lot like it's 1.5. It's really pi over 2. And the reason is, of course, tangent of pi over 2 doesn't exist. As your angle gets closer and closer and closer to pi over 2, then the tangent of that angle gets larger and larger and larger. Okay? The same thing happens in sort of reverse. As I let n go off toward minus infinity, you see that the graph heads down toward negative pi over 2. Okay? So inverse tangent of 0 is 0. Well, it's easy enough here and here. And inverse tangent of n, well, as n goes off to infinity, we get pi over 2. As it drops off toward minus infinity, we get minus pi over 2. So these two pieces look like 0 minus negative pi over 2. Well, that's convenient because the two negatives are about to cancel. And then I get pi over 2 minus 0. So altogether, 2 pi over 2's, which add together give me pi. So this integral converges. And the integral turns out to be just pi. Well, one more kind of improper integral we need to talk about is something like this. Now, this looks nice and harmless, right? This looks super harmless. Um, if you didn't know that this was supposed to be tricky, then you would just, what, integrate 1 over 1 minus x. So what would that be? That'd be like natural log of absolute value of x minus 1. And then you plug in the 3 and the 0 and subtract them, and you're on your merry way. Problem is, right, something odd happens if I graph this function, right, and look at what happens between 0 and 3. You see the problem, right? This thing's got a vertical asymptote at 1. So right here, right, my function x minus 1 isn't defined when I plug in 1, because I'd be 1 minus 1, I'd be divided by 0. So I get this vertical asymptote that happens in the graph right here when x is 1. Okay, well, what do I do about this, right? First thing is I have to be aware of it because this looks like, you know, so nice and simple and innocuous, and wow, they finally gave me an easy problem, and you're telling me it's weird and hard, and I have to do something complicated. Well, yeah, this is Cal 2. That's that's the way life is. So always, 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 when you have something that looks like a normal sort of definite integral, check to make sure that it's not one of these improper kind of integrals, which means check to make sure that the function's continuous. There's not an asymptote happening between the limits of integration. So if I had the integral from, say, 2 to 3 of 1 over 1 minus, sorry, 1 over x minus 1, integral from 2 to 3 would be fine because, 2 would be here and 3 would be here, and I'm completely avoiding the problem that happens at 1. But obviously, to make an example that works out the way I want it to, I had this integral start at 0. So when I go from 0 to 3, that includes the area where I've got my vertical asymptote. So always check to make sure that you don't have that kind of vertical asymptote going on. If you do, then you have to break this up like we did the last example into two different pieces. We'll break it up on the left side of the asymptote and we'll break it up on the right side of the asymptote. So like this, we'll integrate from 0 to, say, capital N, and then let the capital N go toward 1 from the left. So it may have been a long time since you've seen limit as something goes to something from the left. So that's what that little minus sign is. Limit as n goes to 1 from the left. We integrate from 0 to capital N. That's going to find this area here on the left. Okay? On the other hand, the limit as n goes to 1 from the right, and then we go from n to 3, is going to give us this area here on the right, this piece. Okay? So we're splitting this up and letting the n go toward 1 on this side from the left and on this side from the right so that we can see what happens in each piece separately. Again, we have to do each piece separately because we have this asymptote in the middle that breaks everything. Okay, well, the integral itself actually isn't too hard because 1 over x minus 1, you integrate that, you get natural log of absolute value of x minus 1. So when I plug in the n, I get natural log of absolute value of capital N minus 1, then minus natural log of absolute value of 0 minus 1. And of course, the same thing happens on the right, only I plug in a capital N and a 3. Okay, well, we said a few minutes ago that when you plug big numbers into natural log, you get big numbers out, right? But what happens here when I'm plugging in, well, this capital N, right? So as n gets really close to 1, what's happening inside here is like 1 minus 1. This is getting really close to 0. Looks like I'm trying to take the log of 0. Right? Over here I have log of 3 minus 1. That's a 2. That's not a problem. 0 minus 1. That's negative 1. But notice the absolute values. This is one reason why absolute values are so important. This is the absolute value of negative 1, which of course is just 1. So that's easy enough. Those are just regular old numbers. Everything's fine there. The problem is right here. What happens when I try to take the log of something close to 0? And again, you may not remember what the graph of log looks like. You should. So I'm going to show you and make the comment that if you don't remember what this looks like, then remember it now. So here's the graph of natural log. Again, if I plug in big numbers, the graph gets bigger and bigger and bigger. Kind of slowly, but it does get bigger and bigger and bigger. As I plug in numbers close to 0, though, this drops like a rock. Very quickly, it starts dropping and getting smaller and smaller and smaller. So what happens is, as I plug in numbers close to 0, I'm going to get numbers that get smaller and smaller and smaller. So this is going to head off toward minus infinity, which means the whole thing diverges. Okay, well, that's kind of interesting because it means that this area under here, even though there's some positive area here and some negative area here, if we let them cancel, right, maybe something would happen that we don't intend. That's not the way this has to work, though. We need both of these pieces, both these areas to be finite, and they're not. Right? So it's probably worth me waving my hands here, and which you can see. Everybody see I'm waving my hands? Yeah. Waving my hands and making a big deal out of this. This thing diverges, but if we hadn't realized this was an improper integral, of course we'd get the wrong answer. Because the obvious wrong way to do this would be just to integrate 1 over x minus 1. You'd get log of absolute value of x minus 1. Then you plug in the 3, you plug in the 0, you subtract those. It ends up turning out to be like log of 2. This is bad. I mean, bad, 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 bad. Right? This is the obvious wrong answer, and I'm making such a big deal out of this because I don't want you to make this mistake on the exam. So whenever you have an integral that looks sweet and harmless and oh, there's nothing really wrong with this one, look, it's just a nice simple integral that of the kind we did back in Cal 1. If it's happening in Cal 2, then there's something wrong with it, right? Almost always, these kind of integrals on a test are there because they're improper integrals. And the thing to do is to look between the limits of integration, in this case 0 to 3, and see if this thing has a vertical asymptote. Look and see if there's a place where the denominator is 0. If there is, then we're going to have to work it this way as an improper integral. All right, one last example, and this is just way, way, way too cool. This is one of my favorite examples to do because it really drives home the fact that when we start messing around with infinity, you have to be super careful. So one of the reasons why it took so long for people to discover calculus, I mean, most people don't get a lot of history of math in their high school math classes, but the Greeks had figured out all sorts of, well, almost all of geometry. All the sort of Euclidean geometry came from Euclid. That was, what, 300 BC or so. So the Greeks knew all sorts of stuff about geometry and triangles and all of the way that worked. Algebra took a little longer because it took a while to figure out what the right way to write it all down was, to get the notation down so that people could understand what they were doing. I mean, if you're trying to do math with Roman numerals, for example, that's a real problem. So it took a little while to get the notation figured out so that you could graph things and you could do some algebra. But one of the really big problems people had was the fact that they couldn't figure out how to deal with infinity. And this is all over calculus, right? We talked about a few minutes ago that the whole point of an integral was you break things up into little pieces and then use more and more and more and more pieces. You never actually use infinitely many pieces. We just use more and more and more of them as the, what's the right word, limit goes off toward infinity. And so this idea of limit and messing around with infinity was a big deal and caused people all manner of consternation. And this example will show you sort of why that was such a big deal. So here we go. Let's take 1 over x. So we've already done um, 1 over x um, as an integral. But what I want to do is take this graph of 1 over x and I want to rotate it around the x-axis. So remember we've already done washers and shells and all this sort of stuff. So here's one more example of all of this. I want to take the graph of 1 over x from, say, 1 off to infinity and rotate this around the x-axis. Okay, and when I do that, well, let's think back to the previous work on washers and shells. I'm going to cut it this way so I can integrate with respect to x. And that means I'm cutting it perpendicularly to the axis I'm rotating around, which means I'm going to get washers or discs is what the book will sometimes call it if there's no actual hole, which is what happens in this case because there's just one function. So in this case, the volume turns out to be, well, pi times the radius of my cross section squared. What's the radius of my cross section? 1 over x. So I get a circle here with radius 1 over x. So pi times 1 over x all squared gives me the area of my cross section. Dx is my thickness. And I say that that's pi. Okay, you could go through and do all the calculations to see that you get pi. Or if you remember the very first example we did back in when we first started trying to explain what these were, the very first example we did was 1 over x squared. And we showed that when you integrate from 1 to infinity, 1 over x squared, you get 1. And so multiplying by the pi, of course, means we multiply by pi. So we get pi times 1. So the volume of this thing that goes all the way out to infinity, okay, this is called Gabriel's horn because you can sort of see there's an opening here and then this gets skinnier and skinnier and skinnier as it goes out toward infinity. The volume of this horn that goes all the way out to infinity is pi. Okay, now let's do surface area. Okay, well, surface area turns out to be this. Okay, so remember how surface area works? We would cut it and make a little peel here along the surface area. So what we need is 2 pi times the radius, right, to find the circumference of my peel as it goes around. So the radius here would be 1 over x. So I get 2 pi times 1 over x. Then I multiply by the arc length, right, and that is square root of 1 plus the derivative squared, and then dx. So the derivative of 1 over x, well, we treat that as x to the negative 1. The derivative would be negative x to the negative 2, or negative 1 over x squared. So there we go. Wow, that looks nasty. I mean, even in a chapter where we're dealing with nasty, awful integrals, that's a pretty nasty integral. There's no, there's just nothing, right? I mean, no substitution is going to work here because when I square that 1 over x squared, that's 1 over x to the fourth, and all I've got is a 1 over x outside, so substitution isn't going to help. It, yeah, it's just nothing. Um, what are we going to do? Well, the um, the line of reasoning I'm about to explain is the kind of thing that we're going to be talking about a lot once we get to series in the last third of the class. So if you follow what we're going to do now, it will help a lot in understanding the way we're going to work on things later. So here's what I'm going to do. See if I can convince you of this. What happens to this square root, right? If I plug in numbers, between 1 and infinity, well, I've got the square root of 1 plus something ugly squared. So whatever this ugly something is, it's negative right now, but whatever it is, when I square it, it'll be positive. So this is 1 plus something positive, right? So in other words, I'm taking the square root of something bigger than 1. Maybe a number like 2 or 3 or 1.5 or something. And when you take the square root of a number bigger than 1, of course, you get something bigger than 1, right? Because the square root of 1 is just 1. square root of 4, right, that'd be 2, right? So I mean, sort of easy to convince yourself that the square root of something bigger than 1 is actually bigger than 1, which means that if I look at just this part, the 2 pi and the 1 over x, what the square root is doing is making this integral bigger than it would be if that square root weren't there at all. In other words, if I were to take this square root away, okay, then I get an integral that's smaller than I would have had otherwise, right? Because I'm multiplying right now by the square root, and the square root's bigger than 1. When you multiply something by something bigger than 1, you make it bigger, right? So this square root is making the integral bigger than if it weren't there. And if I look at what it would be if that square root weren't there, actually this starts to look familiar because, well, without the 2 pi, right, this is exactly an integral we already did. In fact, the second example we did was just 1 over x dx, right? And what we saw was the integral of 1 over x dx diverged. And of course, this integral is even bigger. So we got an area that was infinity, right? Or an integral that was infinity when we tried to integrate 1 over x. This guy's even bigger because I'm multiplying by something even bigger, which means that this is even more diverging, if that's a word. This thing is even bigger than the infinity we got last time. So this surface area integral diverges. And again, I'm not going to calculate this integral. I just want to argue that whatever it is, it's bigger than the integral of 2 pi times 1 over x. And we knew that the 1 over x integral diverged. Okay, wow, that was a lot of thinking really hard, right? So we could calculate the volume integral, or we just remember that we'd already done that example, and we got pi. The surface area integral we couldn't do, but we could figure out that it was bigger than an integral we already saw diverged. So this is even bigger than the first infinity, and it's got to be infinity too, so it diverges. Okay, cool. What does this mean? Well, if you stare at this for a second, this is weird. I mean, this is way, 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 way weird. Right? What we've got, this horn, if you think about it like it's a paint can, this is a paint can that you can fill up. The volume of this paint can is pi cubic units of paint, right? So I could take pi cubic units of paint, pour down this horn, and it would completely fill it up. But if I wanted to paint it, right? If I actually wanted to paint this paint can, the surface area is infinite. It would take an infinite amount of paint to paint the outside of this horn. That's really cool. And this is the kind of cool stuff and weird and freaky stuff that shows up when we start playing around with infinity. And as I said before, this is a step toward the kind of weird and freaky and strange stuff that we're going to think about when we get to the last third of the class and we're talking about series.